And let's okay, here we go. So in this second part of the course, we are mostly doing with the reverse of the derivative. Okay. So most of the operations in mathematics come in pairs. Okay. You have a additions, and then the counterpart you have a subtractions. Okay, so the inverse of the addition. And then you have multiplications. Then you can define also the divisions. Okay, so exponent, and then you have a logarithm to take the exponent out. Okay, so some of the operation has no counterpart like limit. Okay, so what's reverse of limit? Okay, so we don't have such a counterpart for limit. But on the other hand, we've been talking about derivatives. Okay, so finding from function, from position, we find the instantaneous speed, instantaneous rate of change. Okay, so derivative, and we know a lot. Well, quite a lot of formulas for computing derivative. Okay, so now the question is can we somehow reverse the process? So is there any inverse to that derivative? So that's the main idea uh, we would like to discuss for the rest of the semester. So the problem is find the inverse of differentiations. So what's differentiations? Okay, if you have a given of functions and somehow you have a process called a differentiations, and as an output you get what we call derivative. This is derivative. Okay, so the thing is it possible for you to feed the function here and you come up with a functions whose derivative is that functions? To reverse the process. Mean reverse the process. Given a G, okay. Find F such that prime is G. Okay, so here's given G. Now you need to find F here. Questions. So if you plugged in F to this box, you come up with G. Okay, so it is a reverse in the sense that you in derivative, you start with thing on the left. Let's give an F, and then use the differentiation process to find functions on the right. That's F prime. That's derivative. Okay. Now the problem now is finding or given a function here on the right hand side. Somehow you won't like to find functions on the left-hand side. So you end up with these relations. Okay, so reversing the process. So in that sense, it is called, if such G exists, sorry, if such F exists, it is called antiderivative. Okay. So the reason for the name antiderivative is apparent because that's reversing the process of derivative. So that's the thing that we would like to find. So antiderivative. See, there's that thing. Okay. Is the screen here already? From the textbook, antiderivative, these definitions here?
Yes, sir.
All right. Okay. So this is the definition of antiderivative. I call the capital F is antiderivative of F in the interval. Also, not necessarily for the whole real numbers, but it is enough sufficient in just for the small interval. Okay. If derivative of F, capital F is the small f. Okay, so you have a process here, differentiations, call it diff. Okay, so uh, given f here, okay, so you need to find capital F here. Okay, so when you feed into the process, this capital F, you end up with this f, small f. Okay, so this is called the antiderivative. Okay, so let's back to this one. All right. So somehow the antiderivative, if it exists, what's wrong with this one? Sorry. A little bit messed up with the. Okay, here. If exists is not unique. Okay. If say capital F is antiderivative, of F, that means F prime is capital F prime is F, then any constant derivative, sorry, antiderivative. Okay, because if you take derivative of this, right? So this give you f prime, and this is a constant. So you take derivative, that's 0. Okay, here's derivative. So for k any constant. Okay, In fact, you have this one here. Just the figure. Okay. This is theorem B from the section of the last section we have. That is the mean value theorem. Okay. So in fact, this is from the mean value theorem. So if you have two functions, okay, which has the same derivative, okay, so you have capital F and capital G, okay, so which has the same derivative, okay, F prime equal G prime, and then what you know is that F and G only differs by a constant. Okay. So how you see this one here? Let's see. So you write down. In fact, any two antiderivative differ by constant. Okay, so how we see this one here? Okay, so let's see the difference. We try to convince you by showing that the difference is really a constant. The difference. Okay, so what we'll show is that Cx is constant. Okay, so how we do this one here? Okay, so let's fix a number. A, say x. Okay, so what we're looking at then, an x real number. So what we're doing here, let's compute this one. Okay, so by mean value theorem, that is MVT, right? So that tells you that, well, that must be a prime, right? Not really x, say, but this is say at alpha times the difference, x minus x naught, or some alpha between x and x naught. Okay, but see, what is this? But we know that cx, c prime is that which is by assumption is 0. Okay, so what's the conclusion here? Right, so by MVT, this is 0, then this should be 0. That means Cx, C of x, equal to V of x0 for any uh, for any for any x. Okay, so let's say this is called C, okay, because that's constant. So that means that C is constant, Cx is constant. Okay, so that means f of x is actually g of x plus that. All right, so that meaning It tells you about this one here. So if you have an antiderivative, f and g, okay, then the difference of two the antiderivative is a constant. Okay. So that means conclusion if of f, then general form of antiderivative is all right. So this is for something that you won't find in any marketing theory. This is defining marketing because, well, in the marketing, you used to have this. Buy one, you get two, for example. You get a bonus, something here. Buy two, get three, buy two, get five, whatever. Uh, in this antiderivative, you get one antiderivative and you get infinitely many. Okay, so that's what I told. I mentioned it is defying any marketing. Because you get one, buy one, you get infinitely many. Okay. So now the question is, how do we find antiderivative? For example, okay, then say this is a antiderivative. Hold on. Yeah, antiderivative. Why? Because if you take derivative, dx of, right? So dx of this number, this gives you, let's see, multiply by 6 is 4x sine cosine. So this is equal to this. That's all cap F. This. All right, so we see that also that well, say that another antiderivative, for example, should say capital. Plus one is also an antiderivative. It's F. Okay, because you take the derivative of this one, that's zero. This gives you this one. Okay. So this part, I would call this is a principal part. So differ in just concept. Okay, so antiderivatives has equal principal part. Equal principal part. So the difference is just constants. Okay. And let's see what else. Hmm. Questions? Okay, so here. Okay, so the question is now, uh, what are the formulas for antiderivative? How to compute antiderivative? And I think that's easy because we only compute the principal part. Okay, and plus constant. Okay, okay, so let's see how to find this. Okay, for a polynomial, say polynomial. Okay. Remember, if you have a differentiations, if you feed in x to the n, you get, let's see, x to the n times 1. Okay, so the thing is how we reverse this rule here. Okay, all right. So this rule, if you describe verbally, okay, so what you do from x to the n become n times x to the n minus 1. So what you do here is, well, how you describe this one to become this? How to describe it? What is the first step? If you need to describe this verbally in words, how to describe this process? If you need to tell your friend about this formula, what to do first?
Multiply the x by the value of the power.
Yes, well, multiply by this n. N is the power, right? So multiply by the power. And the second?
Subtract the power by 1.
So I would say reduce power by 1. Okay. Now, if you would like to reverse the process, then it's easy. Just looking at this discrepant here. Reverse. Of course, if you reverse, then you start with 2. 2 and the reverse of 2. Reverse of 2 is, oh, sorry. So the 1 here reverse is reverse of 2. What does it mean? Here you reduce the power by 1. So the reverse is increase the power. Right? Because you decrease the power by 1. Now you increase power by 1. So plus 1. Okay. And then the 2 here is reverse of that thing. Just put so you understand my notations. The power minus 1 is the inverse. Okay. So just like the inverse of the step 1. Step 1, you multiply by the power. Okay. Here we have you multiply when you divide by also the power. But the power here is not the old one by new power. New power is the one that's already increased by 1. Okay, so this means if you have x to the n from here, okay, and you would like to reverse the process, this is the so you would like to get this formula here from this process. Okay, what they say is increase power by 1. Increase by 1. Okay, and then divide by new power. So 1 over new power is n. Okay, so we check here. This is the principal part. That's derivative rules for derivative multiply by power. So that's just 1, and then reduce power by 1. Right, so that's how you do, how you find it as well. In fact, this is not only applied for I mentioned here is polynomial. It's not necessarily it's x to the n and integer, but n can be any rational, for example, or any real number. Okay. All right. So you have also what we call linearity. Derivative. Okay, so if you find antiderivative of f plus g, for example, okay, is okay, where this capital F is antiderivative of f, capital G is the antiderivative of g. So with additions, just compute 1 by 1 and then just add. Also in this one here, if you antiderivative of a constant times f, then the antiderivative is just alpha times the antiderivative. All right. So what is saying what the rule saying is that the linearity is saying is that you can interchange the process of antiderivative with additions with a multiplication by constant. So you can add first and then take the antiderivative, or you can find the antiderivative of each function first and then add them later. So that's reason we another example is, so we now have a, so given this f, that's okay. So antiderivative is, say this is 5, this is 7, right? You can uh, take antiderivative of each of this, okay, using rule that we have so far. Okay, so this is a, so 5 remain 5, but then increase by 1, right? Increase by 1, there's three halves become 5 halves, and then 1 over power 5 halves. Okay, and this one here, x negative 1/2, because it becomes 1/2, and also just 1 over 1/2, that's 2. Negative sine x, so that's give you plus cosine 7 cosine x plus pi, for example, because this constant, so it doesn't matter. This is also antiderivative. Okay, I forget to mention that this rule here, remember, we have this 1 over n plus 1. So that means that n cannot be negative 1. So the question is, what is antiderivative of 1 over x power? So here it is. Okay, so we'll deal with that later on. But this is how we find the antiderivative. All right, some more formulas for antiderivative. Antiderivative. Okay, that's power rule. We know that one. And we have also, let's see. Okay. All right, so what if we have this one here? This direction give you, okay, or just this. This is the composite functions, and plug into ddx. By chain rule, this gives you f prime, so derivative of f prime, so f prime, computed at g times derivative of g. That's chain rule. So the question is, what is the antiderivative gives you this one? So for example, if you have something that looks like this one, let's just make antiderivative of of f, for example, notations. Introduce notations is called right, so that we don't have to write the antiderivative over and over. So the question is now is the, so for example, antiderivative of this formula is increase power by 1 and divide by the new power plus this one plus constant, if you like. Okay, so this rule here says that antiderivative of f plus g is antiderivative of f plus antiderivative of g. Antiderivative of alpha times f is alpha times antiderivative of f. Okay, so just a short notations. Okay. All right. So let me give you example here. All right. In this case, antiderivative. Let me just give you. There, or give you. Okay, so we see this. This one here is. We observe that, well, this 2x is the derivative of x squared. Okay, so this is actually say cosine of, say this is x, and this 2x is just u prime. Okay, so this is the form of, say, this one here. U cosine u prime cosine. Okay. And so the antiderivative is just, let's see, what is the antiderivative of cosine? What functions, if you take derivative, become cosine? So you know that's going to be sine. Okay, so this gives you u. Okay, so this looks like a substitution method, actually, what we call. U equals to this one here. And u prime is, so you get this one here. So 2x cosine x squared becomes u prime cosine u. And the derivative of this is just sine u. Okay. And this is nothing but sine x squared. Any questions? All right, so Let me introduce another notations again. This is Leibniz notations. For the general notations, sorry, general antiderivative. F is this here. Generally, this is called the indefinite integral. All right, so using these notations, well, this is like a S, something like this. This is, but these notations we'll see that in the next chapter on the definite integral. Why is this notation here? And dx, we know that dx is this is sum, this is differential. Okay. So we're summing differentials and we get the whole thing again. Remember that differential is small thing. All right, so this indefinite integral. So using these notations, we have this rule here. Integral of prime x. Say this one. Oh, sorry. What's the problem? Cosine, right? Okay. Is this is what we call a this is, later on explain. This becomes sine u. Right to see because it is general formulas for antiderivative. Okay, so for this one, actually the how you compute this one. Like looks like this one. This is just f. And this is what we call substitution method. How we call substitution method? Because we let u equals g of x here. Okay, and so compute differential du. How we compute the differential? We know how to compute differential. G prime times dx. Okay, so using this substitutions, you have this one. There we go. That's your du. So this becomes indefinite integral. So this is du. Okay, so then this is just say f of u. And this means f of gx. Okay, so what we conclusion here is that this substitution method is really the inverse of chain. Okay, so going for function to derivative, you have chain rule. So when you're reversing the chain rule, you get this substitution method. Okay, so these conclusions. Substitution method is the inverse, but input, not really inverse in that sense. Inverse of the chain rule. Okay. All right, we'll do some more computation with this computing antiderivative. Okay, so we'll take a break for 5 minutes. Okay, stop sharing.